All righty, let's talk a little bit about solving equations on a very basic level. I'll just put an equation up here and we'll set it equal to 0. And talk about some of the principles involved in tackling solving equations. All right, so let's look at this one. Well, I think it would be helpful, everyone, to view it from that context for starters. It's pretty obvious, I think, that if you're subtracting something, if you're subtracting 7 and you want to get 0, then this blob here had better be 7. I think we're tackling any rocket science here. All right, so what's the first step? Well, the first step is to move this blob to equal 7. Seems pretty logical. Now, a deeper dive into that would suggest that a statement like 10 minus 7 equals 3 appears to be equal to 10 equal to 3 plus 7. And it's so obvious that maybe not enough thought's given to what just happened. What we did was we used an inverse operation. Subtraction of 7 becomes addition of 7. And I think most of us can add 7 to some number and maybe not need a calculator. Maybe we don't even have to show. Maybe we don't even have to show addition of 7 and addition of 7 to both sides of the equation. Because if we have to show both sides of that, I'm sorry, I don't think we're going to make gains very quickly. So, step 1, subtraction of 7 becomes addition of 7. All right, now where are we at? Well, you know, the order of operations here is parentheses, squaring, multiplication, subtraction, which seems to follow a somewhat, I think, basic thought process of hard to easy. You know, once we do parentheses, we're squaring, multiplying, subtracting. I think squaring is harder than multiplication. Historically, it probably came along a little later on a piece of paper. Multiplication, I think, you know, had to do a lot of addition and subtraction before multiplication tables appeared. So we seem to be following this timeline of harder to easy. Harder to easy in terms of evaluation. So solving is the inverse of that. We are going to go from easy to hard. At some level, I think that's true. So, once again, we have a blob. This, try to erase it in a moment. We're multiplying by 2, and we're getting 7. Might have been more helpful if I used an even number here for some folks, but I think we can handle this. I think this has to equal 7/2. Multiplication, the inverse, division, and we probably can put 7/2 in here and see why that is true. And so what's that mean? It means that this stage, we'll get rid of this, clean it up a little. Seems that we can get at this blob, multiplication, division. Now the next step's a little bit harder, and most students have not yet answered correctly. Getting halfway there quickly, that was very quick, but we have looked at quadratics with the symmetry, and oftentimes there are positive and negative x values that solve equations like this. So the next blob is something squared equals 7/2. Well, it seems to me that remembering the plus minus, biggest challenge for us at this stage of the term, I think we need an inverse operation. I think squaring gets us positive. I think squaring the square root is an inverse operation. And I think performing it leaves us with something that's true. So that's the next step. And that leaves us x minus, well, I guess I gotta do it here, little space. So doing the squaring becomes square rooting of the other side. And now we're basically home free. Obviously, if we want this answer, then 5 doesn't work. So we got a blob here, and you know what? That number doesn't work, so we get rid of it. It's gone. What does work? That. So another inverse operation. So we've got x minus 5, so therefore x is equal to 5 plus or minus the square root of 7/2. Now in class, I've been giving you this picture and asking you to solve from the standpoint of knowing what you're doing. So let's go to the picture that's associated with this problem. And then I'll erase this. 5 minus 7, a value of 2, equaling a y value of 0. Boom, it's gone. And give it a little thought. Where are we and where do we need to go? Well, right now, this equation has a y value of -7, and we want to get to these x values. First thing you have to do is you got to go up 7. Okay. So we got an x that got something to do with going up 7. And if we're going to multiply by 2, I think we only want half of this, because we're going to double that. And signature squaring means that if we square that, well, we won't get the number we want. So I think the inverse operation of squaring comes into play. And we're at the number 5, and 5 doesn't work. So we got to get rid of it. Oh, we have to measure from it. The bad statement on my part. So what really happens at this point is we know where we are here. We have to move to the right and move to the left in order to do what? In order to do these operations. And that was a better way to say that. A little awkward here. All right, but hopefully that makes some sense. And so hopefully you can see now when we put this in the equation, the inverse operations that take place. So right now we have x minus 5 squared minus 7, and we're going to see if that will take us to 0. Well, first thing is we replace the x with the 5. Oh, that's good. These are now gone because it don't work. And we bring in the square root of, we get that a little longer there, 7/2. All right, let's go through it. The 5's cancel. When you square the square root of 7/2, you get 7/2. The 2's cancel. I've done the squaring. Oh, and 7 minus 7 is 0. This is what we're working with when we have an isolated x in an equation. So let's look at a variety of equations. And of course, you need to know the inverse of those equations. So we have f of x, and we have the inverse operations. And we're having a little trouble understanding one in particular. Exponential problems. And we're having a lot of trouble there. And you have to think about it. And you have to come to the realization that that's the inverse of this. And if you have an x and a y, keep it simple, a 2 and a 9. I hope everybody can see 3 squared is 9. And you're trying to learn how to say it in the inverse. Base 3. What do we start with over here? The 9 gets us a 2. And there's different ways to perform these calculations. Sometimes, however, you do need a calculator. Because what if we made this a 10? Well, I don't know what to use to get a 10. I have to go to a calculator. And if I want to find that value, then I've got to put that in there, and I would assume it's going to be just a little bit bigger than 2. But I don't know what that is. I'd have to find it. But once I found it, then I could put it in here, whatever that number is, just a little bit bigger than a 2 would get me a 10. Right now, we're not going to the calculator. We are just looking at situations like what gets me 1/3. Yes, and that can be rephrased. What on top of a 3 gets me a 1/3? And many of you know now, and many of you don't. I'd like you all to know that that's -1. That there's a factor of 3 one time in the denominator, and this is how we communicate that to each other. All right, so basically, equations that are in one variable, like 2 log base 3 x plus, I don't know, 7 equals, well, let's get something nice here, 15. All right, what are we gonna do? Well, I don't want you to do -7 -7. I want you to do it in your head, and you're allowed to do that in my class. 7's gone. Multiplication by 2, I don't want you doing division by 2 division. I expect you to know that 8 divided by 2 is 4. That's gone. Oh, we need the inverse of log base 3 to the x. Well, I don't think a lot of you probably can get this quite yet unless you keep thinking about it, but it's simply 3 to the 4. So the inverse of logging is exponentiating. I would say few of you in the class know that's 81 right off the bat. And so therefore that's our x. We can check it. 81, what's the exponent you put on top of 3 to get 81? 3 times 3 is 9, times 3 is 27, times 3 is 81. That's a 4. 2 times 4 is 8, plus 7 is 15. And with practice, I'm hoping you can do that quickly and easily, and that you understand what you did and why. Now, it can get slightly more complicated, but certainly problems like 2/3 x minus 5 plus 7. How do I like to solve a problem like this? I don't know. Let's just make this 10 again. All right. I'll take 7 away. That's going to be 3. I'll multiply next 9, and then I divide. I prefer to kind of, instead of the Algebra 1 textbook saying multiply by the reciprocal, I want to highlight inverse operations, and therefore I think that's fairly basic. What else we got? So we got the linear. We got, I'll do absolute value a little differently, and I haven't taught you how to do that yet, but sometimes calculations get a little more complicated, like, I don't know, let's do 5 to x minus 7 over 3 plus 4. Let's get something that's nice here, 44. Okay. Now, this is the argument of a function. Basically, we have m f of x plus c type of equations. We'll set it to 0. So you've got minus c divided by m. Let's see if I can bring it down this way. Minus c divided by m, and then the inverse of that. That's the kind of thought process that we're trying to engender here. So a problem like this has a little bit more complication in that let's do f of ax plus b over c plus d, something like that. Well, we still got an inverse, 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 and then we might have to do some more inverses with the argument. But it's still a standard process. So let's do this one. Subtract 4. Oh, you hit the space bar, obviously, before you do any, hear me out. All right, so that's 8 divided by 5. Oh, here we are again. 2 to the x. 2 to the x type problem. I'm hoping that maybe you got this right this time over here, because you heard it again. What's the exponent you put on top of the 2 to get an 8? Well, that's a 3. So now we've got this gone, this gone, this gone. We're going to multiply by 3. There's our 9, that's gone. We're gonna add 7, 16. And now I hope we're beginning to move into the category of, oh, that's not so bad. Yes, there are a lot of equations that we cannot use this process for. And that really takes us to factoring. All right, sometimes and completing the square is really moving equations into this position to be solved. All right, we're practicing that as well, a variety of practice here. So x squared plus 6x plus 11 equals 0. Well, that's a problem. All right, because you know, we don't have an isolated x. We can isolate x pretty easily. Let's put the 11 on the other side. Right? We can isolate it. And then what do? We add 9, there's -2. We take the plus minus square root of -2. You're going to learn that that's imaginary. A bad term for what's going on, I think. And then addition of 3, subtraction of 3. And I'm hoping that that will make sense to you in a week or two, because we're going to dive into imaginary numbers soon. And imaginary numbers are no different than any number. Any number is imaginary, the number 2. I don't see it floating around. They represent something. And so these imaginary numbers represent things too. Might as well tell you what they represent. So let's look at y equals x squared. Let's set it equal to 9. Well, there you go. There's your +3 and -3, right? But what if we wanted to hit -9? Well, then we'd have a sign change. And we would be at the same magnitude. And just, you know, we're imagining a sign change. Perhaps going in the other direction. That's a good start to thinking about this stuff. All right, so let's see if is there another equation that cubics, certainly cubics are falling into this category. So let's look at 4x cubed minus 7 equals 100. All right, so 107. 107 divided by 4, and the cube root of 107 divided by 4. So let's check that out. Let's put the cube root of 107 divided by 4. Oh, the cube root, the cubing, inverse operations. Oh, 4's cancel, inverse operations, 107 minus 7, 100. Okay, so I guess you have to know the inverse operations of the various calculations we're studying. And that's going to be able to solve tons of problems for you. And then there are some shortcuts for some other problems that we'll be looking at in class. And we're certainly going to try to develop our factoring skills as another method of solving equations. And factoring skills really rely on the fact that it's a very simple concept. Length times width equals 0. Then one of the factors has to equal 0, because 0 times anything is 0. So yes, we're going to get hopefully good at writing sums and differences as products. All right, so I just wanted to put that in front of you. Might as well give you one problem to chew on. So let's see if you can get it. Let's say that we have 7 comma negative 10. 7 comma negative 10 with an a value of 3. And I've seen a few of you in class just write the answer now because you understand what's going on. But for those of you who maybe know how to do this problem more easily now, give it a go. All right, so we're measuring from 7. Yeah, we got to hit a height of, well, we're going to hit a height of 0. I should have said that, hitting a height of 0. So we got to move from 7 left and right. And we've got to go up 10 units. And we're multiplying by 3, and it's a inverse of the squaring problem. And you got your roots. Now, roots are the number that produce zeros in equation. All right, so just put that in front of you. And you really know something when you look at it and you go, oh, that's easy. That's simple. All right, but sometimes it takes practice to get to that point. And here's your practice. Let's give you one more. We'll give you an imaginary one. Okay, and you can try it. It doesn't matter what we set it to. It doesn't have to be set to 0, but we'll practice with 0 here. Let's get this down just a little bit more. There we go. All right, so here we have a upside down. So let's say that a is -2. We have a negative multiplier, and let's hit a height of let's hit a height of 10, and let's have a vertex of 5, 3. All right, so pause the video. I'll just put the answer down and see if it makes sense to you. All right, so 5 plus or minus the square root of 7 halves. And I'm imagining that it's gonna go in the other direction. And we'll be talking about that. I think probably soon. All right, so that's that. I'll post that and give you something to chomp on and something to think about and hopefully make some mathematical neurological gains.